Hey, this video is going to be about chapter 12. And wrong screen. In chapter 12, we are going to start off by talking about linear regression equations. And just to even before that, we're just going to talk about what you know about lines from algebra. So in this chapter, we're going to talk about methods for determining whether a correlation, or in other words, an association between two variables exists, and whether or not that relationship or correlation is linear. Does it make a line? So let's just talk about linear equations. So there's two variables in a linear equation, and they're sometimes related, meaning a value for one can determine the second value. But that's in a perfect world that we would have an exact equation. In statistics, we use those models, but it's not so exact. So for example, parents' height versus their children's height. Okay, so if we were talking about something, let's just make a nice little axis right here, and I was talking about children's heights versus their parents' heights, well, let's just say this is a number order. So the small kids, maybe I should label these axes real quick. I feel like I haven't used this forever because we had a test. Okay, so let's say this is the kid's height, and then this side is the parent's height. Okay, this isn't perfect, but the whole point is that scatter plots are not perfect. So a lot of times, if you have a short parent, oh gosh, that dot is way too big. Hang on, let me delete that. That is ridiculous. Okay, can I just draw? Here we go, just draw. We have short kids, and their parents are kind of short. And usually as the parents get taller, which is up, the kids also get taller. And so they kind of like form this pattern. It's not exactly a straight line. Statistics is rarely exact. Math is exact, statistics is messy. Also, sometimes you're going to have a kid that's really tall, even though his parents are short. Sometimes you're going to have a kid that's really short, even though their parents are tall. So you see how it's just a mess. It's just everywhere. It's a scatter plot. So it's not exact, but you can generally come up with a relationship between the parents' heights and the children's heights because they generally follow a line. So let me just draw a line in here and see it kind of follows along that line. We have some outliers, but mostly on that line. All right, so here we have the regression equation expresses a relationship between x, which is called the explanatory variable. We've talked about this before, but it's in chapter 1. And then the y, this is actually y hat, which is the response variable. So another word for explanatory variable is independent, because that can change. And then another word for y hat, the response variable, would be dependent, because that would depend on whatever x is. So just a reminder from algebra, we have the equation, well, this isn't actually this is from algebra down here. We'll go back to the top for a minute. Now remember from algebra, we had y equals mx plus b, where m was the slope, and why does it say b1? What the heck? Okay, let me fix that. That should say m is the slope. Give me my text back. Give me that stupid dot back. Okay. You know what I'm talking about, right? From algebra. So m is the slope, and b is the intercept, using y equals mx plus b. Well, in statistics, a lot of times we have this equation, y hat, and y hat is just like the estimated value. Like in a perfect world, if it followed this line, what would the answer be? Y hat is the estimated value. And then again, just like down here, let me move that over here so it doesn't get lost. A is in front of the x, so A is the slope, and B is at the end, so it is the y-intercept. Okay, so the graph of the regression. Okay, we'll talk about regression in I think the next video. Okay, so let's just look at an example from algebra. So it says Diane's monthly bill for cell service can be computed using a linear equation. So there's an equation here that we can use. When she uses no data, so like if we were in algebra, we would make a little table with our information. We're not going to do this ever again, but I just wanted to kind of have a callback to something you're familiar with, just so you can see where we're going. So no data, there's our bill price. 2 gigs of data, there's our bill price. Okay, so the first question is, what's X and what's Y? X is independent, so X is what you have control over as the consumer, and Y is dependent, meaning that's what it'll depend on X. So what, I know I'm just saying like the same kind of words over and over again, so let's just put some symbols here. X is going to be the dollars, and Y is going to be the dollars, and X is going to be the data in gigabytes, because you control how many gigabytes of data you use, and then they put it in the formula and they calculate your bill. So here is, oh, I just did number 1 for us. Okay, look at that, I already did number 1. Okay, so independent, we said, was the gigabyte, because we control the number of gigabytes used, and then dependent would be the dollars, because that is calculated. It's dependent on how many gigabytes you use. It's calculated on how many gigabytes you used. So do I need some arrows in here? I feel like I just kind of wrote all over the place. Independent and then dependent. So going back to my little table, we say no data, which could be represented by a 0, is $37.50. That's her flat fee. When she uses 2 gigabytes of data, she's going to pay $45.50. So again, you're not going to make this table ever again. I'm just trying to connect the dots. Connect the dots, get it? Because we're doing scatter plots. Between your algebra knowledge and then what we're doing here. So here's our equation. It's asking for the slope and the y-intercept. So we only have 2 numbers here. So the question is, which number goes where? The number in front of the x is always the slope, and the number by itself is always the intercept. So there's our answers. I'm not going to use m for slope because we're never going to call it m again. Okay, so now we have 2 questions based off of this equation. What is Diane's bill if she uses 5 gigabytes of data? Well, since the gigabytes is the independent, which we said was the x, then I know that x equals 5, and I want to find y hat. That's what it's asking me to do. So I plug into this equation. Y hat, which is the estimated value, is 4 times 5 plus 37.50. 20 plus 37.50 is 57.50. You can put the extra 0, it doesn't matter. Okay. Now it says if Diane's bill is $49.50, how much data did she use? So this time we know Y because we know the dollar amount, and we want to find X. This one, okay, so C was just arithmetic. I just multiplied 4 times 5 and then added to 37.50. This one is going to be algebra. Remember chapter 6 had a little bit of algebra? Same thing here, because if I put in a Y, now let me just tell you right here, this is the problem that people miss on the project and the test the most, because they put the wrong letters in the wrong spot, and then this is what happens. People always want to do it this way. Part C was easy. Everyone wants to do it part C way. So they just force the numbers so that they do it that way, but that doesn't mean it's right. This one, we know Y is 49.50, so that's going to equal 4x plus 37.50, and now I have to do algebra to solve this. So first thing I want to do is subtract 37.50. Let me just find myself. What am I doing? Oh gosh, what am I watching? Okay, I just need to find a stinking calculator. Where is the calculator? Okay. This side over here, but where's my PDF now? This side right here. Okay, good enough. So I have this equation right here, and I'm going to just go to the calculation. There's a way to solve this on the calculator, but A lot of times learning something new can take a lot longer, and it's really not that deep. Like, we're not going to go that hard into this algebra. We're just going to subtract. And at this point, you might even be able to just divide by 4 in your head, and we get that x equals 3. Remember? Okay. So I talked about this example of scatter plots, the parents versus kids. There's all kinds of pictures that we could have here. So the first two are linear. So this one is kind of like my parents' one, where it basically went up. I don't know, where am I? Right? Okay, here we go. Get me my line back. It basically goes up, although there's a couple of random ones. That's X. Okay, there's a couple of random dots that hang out outside, but it mostly follows the line. The negative linear pattern mostly goes down. There's some that are farther away from the line than others, but this is very much just like the slope in algebra. Positive goes up from left to right. Negative goes down from left to right. No pattern is where it really just looks like somebody spilled pepper on your paper. If I try to draw a line this way, every dot is far from it. If I try to draw a line this way, every dot is far from it. No line makes sense, so we say it has no pattern. This last one, there is a pattern. Ooh, it's like a rainbow or an upside-down parabola. It's just not a line. It's not a linear pattern. So we're going to be talking about those three the most: no pattern, positive linear, negative linear. You will see a couple nonlinear just to compare in the future, but mostly this is linear because that's the name of the section. Okay, oh, look at this, more linear regression. So what we have here is stuff that we are going to look at. I don't think we need our calculator. Nope, we don't. Okay, I'm going to hide that. We don't need it for the rest of this. Oh gosh, I always make my lines go every which way, but where I want them to. Okay, stop it. Make it bigger. Okay, making predictions. So we kind of made predictions using the formula, but that was more specific. Like, if you use this much data, you will pay this much. Here we're going to use what's called the line of best fit. It is a line that best fits the data. Like up here, this line was pretty good to just, or this one's even better because all the dots are pretty close to this line right here. It's not exact. Most dots aren't on it, but they're all pretty close and they follow that same slope. So here we have the line of best fit, and you can go ahead and read through those. It just talks about having X's and Y's and whatnot. Okay, so this first example, the table shows data collected. So here we have data from 25 to 50. That's really important to know where what our data is from. So we have data from 25 to 50. And that gave us a score over here. Now, there's an equation that they gave us over here called but it's y hat, which is 0.44x equals 65.2. And what we're going to do, I guess we are going to use our calculator. We're going to use this line of best fit to estimate or the predicted test score of someone who spent 32 minutes exercising. Now, you've exercised before, you've taken tests before. 2 minutes of exercise doesn't really make a difference, but we can kind of estimate where that would land. And so here we have 30 and 35. 32 is in between there. Let me get a brighter color so we can see it. 32 is in between there. So we want to know what that, oh, why is my address posted? Goodness gracious. Now it's a $sign. This PDF is wild. Okay. 32, and then what's going on over here, that's what we're going to calculate. So I have my formula, and it's y hat equals 0.44. I'm plugging in 32 to this 65.2. Now notice minute is over here in the X, and the score is in the Y, just like in algebra. So when it says 32 minutes, I know that I plugged the 32 into the X. Okay, so I'm going to We're just doing algebra, or arithmetic on our calculator today. Next video, or one of them soon, we're going to be using the regression features on here. But this is telling us 79.28. I don't see any sort of indicator of rounding, so I will write that down. Again, that was 79.28. So in other words, 32 minutes would be right here. Yep, I believe it. Oh gosh, it doesn't need to be everything. It makes sense that because this falls in here, this reasonably falls over here. So is this reasonable? Yes, this is reasonable because the data, it makes sense. Reasonable is more like a feeling. Does it make sense to you? Yes, it makes sense. Well, maybe I should have put this. You're going to get mixed up if I cram it in there too far. Okay. Reasonable. Yes, because it makes sense. A little extra than 30 minutes gets a little extra score. Is it reliable? Now, reliability depends on what data we already have. We know stuff. Look at this arrow. I drew it here on purpose. We know stuff from 25 to 40 minutes. Anything inside 25 to 40 minutes we can predict because we know what's happening in that range. For all we know, someone that practiced 20 minutes got 100%. And someone, what are they? They're not practicing, they're working out. And somebody that worked out 45 minutes got a 2%. Like we don't know. It doesn't seem like it, but we don't know because we don't have the actual data to prove it. We do have actual data to prove from 25 to 40. So since 32 is right here in the middle of 25 to 40, we say it is reliable. In other words, it is within the scope of data. And I'm just going to put right here red arrow. Don't write red arrow unless you made your arrow in red, but somehow indicate to yourself that this red arrow here is the scope of data, whatever the X is. Okay, let's do this again. 42 minutes. Where's 42? This is why I wrote on the graph too, so we could see where it lands. 42 is a little above 40. So first I'm going to plug it in. And it is, that was a 42. Get out my calculator. Remember, you can copy and paste just by going up arrow, and then you hit enter or execute. It copies it, and then you just hit over, and you can change the 32 to a 42, and we have 83.68 minutes. Not minutes, what is that? That's the score on the test. 83.68, just to see where it lands on the graph. On the table. Okay. Is this, I'm going to write this bit down here, but I want to look at the table first. Is this number reasonable? If I work out a little more than 40 minutes, will I get a little higher than 83? Yeah, it's reasonable. It feels okay. It makes sense. Is it reliable? No, because once the red arrow only goes up to 40. It has to be between 25 and 40. As soon as you're outside of 25 to 40, the answer is no, it is not reliable. So reasonable is a feeling. So we can say, yes, it makes sense, but no, it is not reliable because it is not within the scope of data, which again is that red arrow from above. So looking back, a little more than 40 equals a little higher test. Okay, that's okay. I believe it. There's enough evidence here to make it feel right. But it's not reliable. We don't know for certain because it's beyond the scope of data. The data is from 25 to 40. Or the scope of data is 25 to 40. The scope of data, also notice, that has to do with the X. So when I say the scope of data, I'm talking about the X. I'm looking at the X. That red arrow has to do with the X. It's getting too close. I can't put them together, but I'm trying to underline. Okay. Yeah, that's it. This is huge. Reasonable and reliable. It's pretty easy once you get it. Reasonable is based off your feelings. Does it feel right? Does it make sense? Reliable is based off of the scope of data. So look at the X's and say whether or not it's within the scope of data. Other than that, it'll just take a couple of problems to practice to get the hang of it. But that is it for this section. That next activity is a little activity for you to try. So that is it for this video, and have a good day. I'll see you in the next video.